let's take a look at 12.6, solving exponential and log equations. Now we started to do this a little bit, I believe early in chapter 12, and we looked at a one-to-one base relationship. So this is where we had b to the m is equal to b to the n, and if the bases are the same, you set the exponents equal to each other. So if we look at my first example, base 5 to the 3x minus 4 power equals base 5 to the x. This is a one-to-one base. One base 5 on the left, one base 5 on the right. They can cancel each other out, and we're left with the exponents equal to each other, and we can solve those. Add over the 4, subtract over the x, you get 2x equals 4. Divide by 2, x is equal to 2. And that's my answer. Again, if you wanted to, you can go to your calculator and check this. So I will take my calculator, we'll clear that out. Let's see, make my calculator a little bit bigger. We'll take 2, store it for x. I type in the left side 5 raised to the power of 3x minus 4, enter, it's 25, and 5 raised to the x power. Well, with x being 2, that's going to be 5 squared. They're both 25, so this is the correct answer. So again, we should be grading. All right, next, you might have to use the conversion rule. 2 to the 2x minus 7 equals 2 to the 8th. These two bases aren't the same, so I'm thinking about using the conversion rule, but wait a minute, stop before we do that. Remember back in the early part of chapter 12, we said you can break this 8 down to 2 to the 3rd power, and now I'm back to 1 to 1, so we cancel the base 2's, 2x minus 7 equals 3, add over the 7 to get 10, divide over the 2 to get 5. There's your answer. So again, if I take my calculator, 5, store it for x, and now I type in the original left-hand side, 2 to the 2x minus 7, and the question said it's supposed to equal 8. Well, there's my 8, so I know I'm correct. Our next problem here, 4 to the x plus 1 is equal to 1 over 32. As you can see, I clicked one too many clicks. We're going to break the 4 down to 2 times 2. The 32 is 5 2's multiplied together. So this is 2 squared to the x plus 1. This is a power to a power, so we're going to multiply those two exponents. 1 over 2 to the 5th, however, this is not one-to-one base because this base 2 is in the denominator. This is in the numerator. So again, we can use our negative exponent to move the base 2 up into the numerator. 2 gets multiplied to the x into the plus 1. It's a distributive property, so 2x plus 2. Now the base 2's are the same. Cross them out. Set the exponents equal to each other. Subtract over the 2. Divide by 2. There's my answer. Now again, if you have a terrible looking answer, well, I must have done something wrong. Again, let the calculator verify everything for you. Negative 7 divided by 2, store it in x. Type in 4 raised to the power of x plus 1. Get out of there. Now we want a fraction 1 over 32, so I'm going to go math, return my answer as a fraction. There's my 1 over 32, which matches what's on the paper, so I now know that for sure is correct. 27 to the x minus 2 is equal to 9. Okay, well, 9 goes into 27 3 times, but that's 9 and 3. Because we hit that 3, everybody breaks down to 3's. So this becomes 3 to the 3rd. raised to the x minus 2 power. 9 is 3 squared. We will multiply that power of 3 to the binomial x minus 2. We're going to get 3x minus 6. Base 3's are the same. Cancel them out. Solve for x. Add over the 6. Divide by 3. 8/3 is my final answer. So these four are examples of those one-to-one base relationships that we kind of saw back early. I think that might have been like 12.2, 12.3-ish. All right, now I have 3 to the x minus 1 equals 14. In order to solve this, remember all my bases with the exponent had to be isolated by themselves. So we're going to take this minus 1 and add it over to the other side. This 3 to the x must be isolated. Get rid of the minus 1. Add it to the 14 to get 15. Now I break this down. That's 3 and 5. That's not a good thing. So now this will not be a one-to-one base relationship. This is your conversion rule. Take it from exponential to a log. That will get the y in the exponent position, which is my x. The y is out of the log function, so that'll get the x out of my log function. So log base 3, 15 comes over to base 3, x goes over by itself. Well, wait a minute. If x is by itself, I just solved for x. This is the exact valued answer. Now, if they want the exact value answer, and they also want a decimal answer rounded to so many decimal places, it's traditionally 4 decimal places. You can go to your base change formula, natural log of the old argument 15 divided by the old log base 3, so natural log of 3. Again, I like to store it for x. Then I test it, 3 raised to the x power minus 1. It does equal 14. So this is definitely my answer. And again, if they wanted the decimal to 4 places, 1, 2, 3, 4, the 7's going to round the 9 up to a 0, and the 4 to a 5. You have to keep the 0. You must have 4 decimal places. All right, if we had 7 raised to the 2x minus 5 equals 43, here's my exponential. It is isolated and by itself. So we'll convert it to a log right now. So log base 7, 2x minus 5 goes to the other side of the equal sign. 43 comes over to log base 7. 43 is in the argument. Now that x is out of the exponent position, we can solve for x. Add over the 5. Don't touch the 43 on the inside. Divide everything by 2. No arithmetic. Again, this is my exact value. Or you can go to your calculator and get the decimal representation. Here's the base change formula for log base 7 of 43. Then I add 5 to it, and I had to put parentheses around the numerator because there's 2 terms up there. Then divide by 2. Store it for x. Type in the left side. 7 raised to 2x minus 5 equals 43. If you were going to use the calculators that I provide, I would probably use the fraction command. Alpha y equals, get your fraction text box, type in what's in the top. Again, you can go to math, scroll down to A, log base. We want 7 as the base. Right arrow out of there into the argument, 43. Jump out, plus 5. Jump down to the denominator, 2. Again, I would still store it for x just in case I typed something in wrong. Notice my decimal representation is the same. And if I type in that 7 raised to the power of 2x minus 5, I hit enter, there's my 43, just like it says on paper. So I now know it's correct. All right, next example. All right, here my exponential is, well, identify the exponent x. X is only on base e. 3 is not part of the base. I'd have to have parentheses around it. So add over the 7, makes that a 30. Divide both sides by 3 to make this a 10. Now convert it to a log. And the log for e is ln. So ln of 10 is equal to x, you go to the other side. And that's my exact valued answer. I go to my calculator, ln of 10, store it for x. There's my long, ugly decimal. Type in 3e raised to the x power minus 7. I get the 23. Then I know this is correct. Round it to 4 decimal places, 2.3025. 8 rounds it up to a 6. Over here, same setup. E to the 3x plus 4 is my exponential. Get rid of the minus 5. Add it to the other side to get 36. Get rid of the 2. Divide both sides by 2. 36 divided by 2 is 18. Now that the exponential function is by itself, I can convert it to a log. So this will be just like we had over here. Natural log of the 10. Natural log of 18. 3x plus 4, you go on the other side of the equal sign. And now we solve for x. We'll subtract over the 4. Can't combine it with the 18 on the inside, just leave it on the outside. Divide by 3, there's my x. So again, if you want to check it with your calculator, good idea here. Let's see, alpha y equals fraction natural log of 18. Close the parentheses, minus 4. On the bottom is a 3. Over to the right, store it for x. There's my decimal answer. Type in the left side, 2. Oh, gotta move this over just a little bit. Second ln, e raised to the power, we'll put in 3x plus 4. Jump out of the exponent, subtract 5 from it. Says it's supposed to be 31. I hit enter. There's my 31. Everything is correct. Very, very gradable with your calculator in this section. All right, if old calculator, base change formula, again, parentheses around the whole top, 2 terms. ln of 18, close those parentheses, minus 4, close the parentheses of the numerator, divided by 3. Same decimal I got, same entry, same check, all good. So these are our exponential functions. Now we're going to go to log functions. Log functions, remember, whatever rules in an exponential form, there has to be the same rule in log. So the logs have a one-to-one base relationship. If you have one log on the left of the equal sign, and that's it, with another log on the right side, the logs are the same. That's a one-to-one property. You can cancel out the logs, and you set the arguments equal to each other. Then you also have the conversion rule as a backup. This is when you will only see one log in the problem, not a one log to one log property. So looking at this example here, log base 3 of 3x minus 1 equals log base 3 of 2. The logs are the same bases. There's nothing else adding or subtracting, multiply, dividing to the outside. Cancel the log base 3's. 3x minus 1 equals 2. Add over the 1 to make a 3. Divide by 3. X is 1. That's my answer. Over here, there's only one log on the left side, nothing on the right side. So we're going to convert it to an exponential. Base 3. 2, you come over as my exponent. 3x minus 1, you go to the right side all by yourself. Well, 3 squared is 9. And now we can solve for x. Add over the 1 to get 10. Divide over the 3. We get 10 thirds. Now, something interesting to show you where you have the one-to-one log property here. Because the log base is canceled out, when I take my 1 and I store it for x, I type in the left side, and you can use any log. So I'm just going to hit the log button. 3x minus 1. Close them up, hit enter. Then use the same common log, put in the 2. Enter. Notice the two decimals are the same. And it works if I want to use the natural log. Again, what will happen here is these decimals will be different from the previous ones because we're using a different log function. But again, natural log of 2. Between my two ln's, those decimals are the same, so I know this answer is correct. Over here on the right, let's see, we solved this, I believe. Whoops, oh no, I lost my calculator. We had that 10/3. You can store the 10/3. Use your log base command under your math button, and you can get your answer checked. I'm seeing if I can get my calculator back up here on the screen. There it is. All right, calculator. There you go. Okay, so again, if we wanted to check this, 10 divided by 3, store it for x. Log base 3, under math, scroll down till you get to A. Enter base 3, 3x minus 1. Close it up. Whoops. I don't need to hit parentheses there because they already have that there for me. Alright, it should equal 2. Yes, it does. I know everything's good to go. It's correct. Next problem. This one here is technically not a one-to-one log property like this one was. No multiplications, no adding or subtracting on the outside. Well, here we have multiplication on the outside. So what we're going to do is we're going to use the power rule to move the coefficients back inside the argument as an exponent. So this will become log base 5 of x squared. This 3 is going to go on the 4 as an exponent of 3, 4 to the 3rd power. So I change it. Now this is a one-to-one property for logs. I can cancel those. X squared is now equal to 4 to the 3rd, which is 64. I take the square root of both sides. I get a positive or negative 8. And, oops, wait a minute. The negative 8 will not work because the argument on the inside has to be greater than 0. So negative 8 is not bigger than 0. Remember, the domain for x is 0 to infinity. Negative 8 is to the left of 0, so we have to throw that out and just keep the 8. My next example, same situation. 3 is being multiplied to the log. Take the 3, put it back inside as a power on this binomial. Just like so. And then we have to condense this down to 1 log. I'm adding 2 log base 2's. That's condensing with your product rule. So this 4 gets multiplied to the binomial x minus 1 to the 3rd power in the parentheses. Don't try to FOIL this. Don't distribute the 4. Leave it alone. Now that we're condensed down to 1 log, you can use your conversion rule. 2 to the power of 5. All this goes over to the right side of the equal sign. So 2 to the 5th is 32, so I'm going to set it equal to 32 over here. We'll divide by 4 into the 32 and get an 8. Then we take the cube root of both sides. Well, the cube root of 8 is 2. Add over the 1, x is equal to 3. Now, if my calculator checking for this one, because my logs didn't cancel out, I have to use log base 2. So if I go to my calculator again to check this, I'll store my 3. 3, store it for x. 3 times math log base a. We'll put a 2 down there. We're going to put an x minus 1 in. Jump out of the parentheses. Plus math option A. Enter. Another 2 for the base. A 4 in the argument. I hit enter. It's equal to 5, just like it said up here in the problem. So now I know I'm correct. Okay. Whoops. Now, wait a minute. Wait. Now we have 2 logs on the left, 1 log on the right. So if I could condense this side to 1 log, okay, back here was the plus sign, so that's going to be the product rule. We condense it to 1 log, then I can cancel my logs. So adding multiplies the 2 arguments inside of 1 log base 10. Now this is a 1-to-1 log property, so I'm going to have to FOIL this out and get it set equal to 3x and then set it equal to 0 to solve. So once I FOIL it out, I get x squared minus x minus 12 equals 3x. Subtract over the 3x, so it's equal to 0. Now factor. What 2 numbers multiply to be 12 and subtract to be negative 4? How about negative 6 and a positive 2? So the answers are x equals 6 and negative 2. And I gotta say, wait a minute. Always check these numbers, especially the smallest. Negative 2 plus 3 is 1. That's okay. Negative 2 minus 4 is negative 6. That's not okay. 3 times negative 2, negative 6. Not okay. So our problem here is that negative 2 will not work. Throw it out. 6 will be fine. 6 plus 3 is 9. 6 minus 4, 2. 3 times 6, 18. Everything is good. On the next example, same situation. We have a minus sign, so we're going to condense this to 1 log by using the quotient rule. Log base 4. On the top, we'll put x squared minus 9. On the bottom, x plus 3. That's a difference of perfect squares. This binomial is part of this factors up here. So cancel the x plus 3's. Log base 4 of x minus 3 equals 3. Conversion rule. 4 to the power of 3 is equal to x minus 3. 4 to the third is 64. Add over the 3, you get 67. And that's our final answer.